Okay, good afternoon all. In the last lecture, we have seen about the image sensors which are responsible through machine vision camera. Basically, we have seen that there are two types of cameras, that is analog and digital. And moreover, concerned with this topic of this course curriculum for machine vision, we mostly use digital cameras because our interest more is to store data in terms of digital means, right? And then later on, we've seen that these cameras, how they help us with uh, different ability to capture the images. Those were line scan cameras and area scan cameras, right? So now here there are two basic parts. The moment we talk about any image or a camera, we need to think of image sensor and the lens. Now, these are the, you can say, important components of a camera. Okay? Any camera will have these two components, image sensor and lens. Now, the resolution of the image is determined by the image sensor. The moment you click a picture, if you want to find out the resolution, that resolution of the clicked picture is being determined by the image sensor. The other component, which is the lens, it determines the focal length of the camera, how near and far the clicked image is, and based on that, the focal length is decided by the means of lens. Now, this is a hardware part. The moment we have lens, there will be different lenses. So the moment we talk about the first component as image sensors, we have two types of sensors. First is the CCD, that is charged coupled device, and second is the CMOS. CCD we have completed in our previous lecture, even though I'll revise it. And the other is CMOS, which is complementary metal oxide semiconductor. Right? Now, these both sensors are used nowadays, but initially CCD was there, and CCD and CMOS sensors work in the same way. Right? Now, these sensors will have a grid of photosensitive cells, what we call as pixels. So when light from the scene gets reflected towards the camera, the light falls on these photosensitive cells, same as light falls in our eyes. Right? Now, the moment it falls on these photosensitive cells, the image sensor gets activated, it collects that light, and then it is converted to electrical energy or charges. Right? I showed you a small video wherein there will be light illumination, wherein all those intensity of light will be stored, and depending on that intensity, you will be able to identify what color it is and what pixel it is, so that you may convert these electrical charges in terms of their capacity into numbers or in an array or matrix form. Right? Now, between these two comparisons of CCD and CMOS, the main difference between these two kind of sensors is that the way their structure is, the grid is, you can see here, this is the grid, right, wherein the light will be incident and the photoelectron will be passed on from one phase to another phase and so on. This will be happening within a millisecond of a fraction of a second, and then these shift register will be holding those values and then amplifying it and then sending it to the you can say the actual circuitry board, the additional circuitry board, wherein you need to have the convergence, as this energy, what we are getting is in terms of electrical energy, right? So there will be some kind of convergence from analog to digital and digital to analog, right? So the way we read this grid might be in terms of rows and columns, thinking of as a matrix, and these each pixel electron will photoelectron will represent as a pixel. Right? So that is the only difference. In CCDs, you can say that the electrical charges are transferred line by line using a circuitry and read like a shift register. Now this is your shift register, right? Now as I said, there will be some kind of conversion of electrical signal. So the output is converted to a digital signal as we are getting the electrical charges or electrical energy from this as an input. So we need to convert it from analog to digital. Now in most, you can say CMOS sensors, na, at each pixel, there are some ICs, right, integrated circuits, which are used to convert the electrical energy to voltage, which is then transferred to the wires. This is the additional circuit board. What we saw initially in that diagram was of CCD, the charged coupling device, wherein we had a proton to electron conversion and the electron to voltage conversion. Now, this is all in terms of analog, where we need to uh, convert the light into electrical energy. Now, electrical energy back again converted from electron to voltage conversion, and that will be passed to the camera circuit board where it will be able to analyze, interpret, read, and synchronize, right? Whatever the data is being provided from this CCD, so that in the final output you may be able to represent an image with respect to pixels, right? The moment we clicked on the button to click an image, we had analog signals, it holds some electrical charges, it had some electrons, and basically applying through some additional circuit board, we get a image. Right now, this is CCD images. There we have seen some of the comparisons between these two. These sensors produce high quality images. The moment we say that it is having a high quality, it requires more power, so it consumes more power and are a little bit expensive. Whereas in CCDs, the chips are specifically manufactured or fabricated to the enable the electrical charges which are to be transported to the chip. Here, if we are having some high quality, we need an extra circuitry for the convergence of analog to digital, which again will require more power, right? And compared to CMOS, these are more expensive. In the conversion, in CCD, the conversion is done after collecting the charges, the electrical charges from the pixels, so that noise will be less here. As the noise will be less, the image quality will be better, right? Again, from CCD, this can be a part of your, you can say, comparison between CCD and CMOS. The charge from one pixel storing in the next pixel can spill, right? That can be leaked. The moment the pixels are leaked, you may get some bright spots because it will be mixed up with the other nearest neighbor pixel. So there might be bright spots created. It can be used in various applications, as in high quality images with high pixel counts. Even though you stretch out your image, zoom out, the pixel quality will remain same. So this will be used in your professional cameras and medical imagery and some kind of scientific applications. Along with this, we need to see the comparative analysis of the other sensor, that is the CMOS sensor. Now here you can see we had a row and column kind of structure in CCD. Here we're going to see that it will be a little bit complex compared to CCD. CMOS here sensors are nothing but, you can say, at each pixel, you can see this is a grid, how we had it in CCD, right? We have row drivers and shift drivers. So this was a part. The moment it was an additional circuit where I need to have shift registers, a timing generator, analog amplifiers, again a timing generators for rows as well as for columns. I need to have a pixel array of 512 into 512. Now these are included on CMOS circuitry. They're not, I can say, a different part as we have seen here in CCD. This this was an extra, I can say, circuit board need to attach to it able to identify the image. Whereas in CMOS we are having this image, those you can say those blocks inbuilt on this board. So it is very easy for us to convert those energy, stored energy in terms of electrical energy, which is then being transferred to the wires. Now here in CMOS sensors, they produce images of lesser quality. Now, to mention a point here, CCD will have a high quality. High quality will need some more power and extra circuitry, whereas CMOS produces image of lesser quality but consume less power, right? And are relatively inexpensive compared to CCD. Hmm. This is the diagram, the actual block diagram of how an image sensor for CMOS works. CMOS sensors can say voltage convergence happens at every pixel, right? That's why we can say the image quality is less due to higher noise. Talking about noise in CCD, we do not have noise. That's why we have high quality images, right? In CMOS, there will be noise, so image quality will be reduced. Consumption of power will be reduced as there's low pixels quality in CMOS. CMOS can provide higher speed for the transfer of charged packets through the chip as the quality is low, consumption of power is low. Quality low means that means there will be less number of pixels. So the obviously the speed of transfer of your pixels of the charge electrical signals from packets in terms of packets via the chip will be more you can say faster compared to CCD. Uh, in CMOS, the integrated circuits are located at each pixel. So the light sensitivity is less. And as not at all, the light may fall on the photodiode also. So here, that is the reason why we have less quality, image quality for these kind of sensors, whereas CCD have high quality, but these are more faster compared to those. You will see further that these both technologies, CCD and CMOS are being used together. That is the high quality from CMOS and faster speed and less power consumption of CMOS. So this will give you us a very good approach while storing the image quality at higher quality, consuming less power, and transfer speed will be more faster. Right. So CMOS approach you can see is very much more flexible, as you can see that each pixel can be read individually. It will not be dependent on any other pixel. So we can say that CMOS sensors are very greater in demand in consumer applications, as in professional digital cameras, wherein we have less exacting quality demands. It is more evolving technology. CCD is moreover not used here. So in future, we may say that CCD in producing high quality images while retaining the advantages of less cost and smaller power requirement may replace CMOS image sensors also. But on the other hand, both technologies, both image sensors are good. So we can have two different circuitries. From one circuit, we can have high quality image pixels, and from the other image sensors we may have a faster transfer rate and less power consumption. So in this way we can use both kind of technologies to, we can say, to to help our applications. This is the actual diagram. Now if you compare both the diagrams, both the image sensor diagrams of CCD and CMOS, you can see that all these blocks, whatever these blocks were on a different circuitry board, right? And this grid part, the way it reads images is on the illumination side, right? There were some capacitors which used to store the intensity of the light and try to convert it into electrical energy. And then it would send to the shift registers and then they will convert it into electrical energy. Now here you can see complementary metal oxide semiconductor will consist of those blocks which were on an external circuitry board in the CCD, right? Now they are included on the circuit board itself. So there is no peripheral or external circuit needed for CMOS to interact to after storing these electrical charges into pixels. Now what we have here is the connector and the bias decoupling. Now this is a camera circuit board. Now apart from this, CMOS here will give you directly an image. It won't require you to have any another, you can say, uh, additional circuit board. So this diagram will let you help understand and tell you the different, can say, points which are related to CMOS and CCD for comparison and differentiation. Hmm. We have one more sensor as TDI. TDI sensors, those are nothing but the time delay integration sensors. We'll see that too. Now, this is a special kind of sensor that is used in line scan cameras, right? Now, there are different camera types. We have line scan camera, area scan cameras. So they have different purpose depending on how fast response must be there from a specific kind of camera, what kind of object it is, whether it is small, big, if it is moving fast, if I need to capture it, is it having some kind of image applications, or it is moreover software dependent. So there are lots of things to be thought of that how could these sensors could be applied in what type of application, right? So this is a special kind of sensor that is used in line scan cameras. Now we'll be seeing that what are these two types of cameras. Just a general idea. Line scan cameras scans one rows of an image at a time. As the name itself says, line scan. So it will be scanning the image line by line. So one at a time, one row of entire pixels will be read at a time. And that's how the pixels will be stored into the memory. The moment we finish reading, image will be stored. Right now, here in this form, the image needs to be quickly recorded because the camera is moving away from the image. Therefore, high light levels are required. If light is not proper, it won't go back because it does not have the capacity to scan the entire image at the same time. It will be reading the pixels row by row. So once the moment the line scan cameras read one row of an image, there's no possibility that it is going back again if it is not recorded any of those pixels. It will leave as it is if it is not recorded. So high light levels are very much essential here in terms of TDI sensors, which will help to store the actual pixels of those image which we need to record. When you say that TDI sensors have multiple rows of pixels arranged as an array. Now, no matter what kind of technology you're using, it will be in terms of matrices or arrays. We need numbers which represent pixels. Hmm? Pixels again, which are in the color palette of 0 to 255. We have total 256 color variations. So if we have such kind of arrangement, any sensor, depending on what kind of application we are going to use, is feasible for our sensors, right? Now there will be a 40-minute session. The moment this session automatically closes, you use the same link to join for the another session. And if possible, I'll be using these two lectures to mark your attendance, which we have missed in the previous lectures. Hmm? So those two will be filled, and one will be for, yes, for yesterday, that is on Monday. Monday we had, where we had to about to have the lecture online, but I was not feeling well. So if I cover two lectures today, the last two lectures will be cooked up here during your mock drive test and training and all, and one remain will be from the this week's Monday. Hmm? Note that the attendance will be marked for these lectures. Hmm. Now here in TDS census, what happens is the image needs to be quickly recorded, right, from the camera as it is moved away. So now this will not be always that, this may not happen always that for a possible or feasible when we are using this in industrial settings, that it will be in a very, you can say, smooth manner. These TDS sensors will have number of pixels, multiple pixels arranged as an array. Now here the arrangement is very important for using any kind of sensors, might be CCD, CMOS, or TDI sensor, or any type of camera, line scan or area scan. TDI sensors, the moment we are using it, camera movement is synchronized with the movement of the object. So the moment object moves on from the conveyor belt, camera will go along with, scan it, or particular scene whose image is to be being captured. Right. Now here, once more than a row in the sensor array captures the same image data, it is possible to obtain a good quality image even under low illumination conditions, right? If we need highlight, then it's okay. But if it is not there, and if our camera moves along with the object or along with the scene, the, the one which image we are going to capture, so it can have more than one row in the sensor array which captures the same image data. Hmm. The moment we say the capturing of the same image data, this is possible for obtaining a good quality image, even under low illumination conditions. So if there's no highlight conditions, you have to capture the same area, that same row in terms of array, so that you can get a good quality image. So this can be achieved the moment your object or scene is moving, along with your camera will also be moving, right? So apart from CCD and CMOS, we have TDI sensors, time delay integration, special kind of sensor, which is mostly used in line scan cameras because it takes time to store an image. If missed due to low light, the line scanned pixels will not be read again. So if my camera moves along with the object, even though I miss or have low light uh, conditions, I can capture the image in good quality, right? So this is one of the, you can say, advantage in using TDI sensors. Now, this is how it actually works. This is a CCD based TDI imaging. Right? CCD we are going to use here in TDI, which is being combined with advanced CMOS. As I told you, instead of having CCD different and CMOS different, we can use these both technologies together to achieve high quality and to consume less power, right? This is TDI imaging, which is being combined with advanced CMOS drivers and read out in one single chip. You can see here, this is my camera, top of here. The scanning direction, again, TDI sensors uses line scan cameras. So one by one, line by line, row of pixels will be scanned. Now the problem occurs in low light, right? So if our camera moves along with the object, it can again have a good quality. Now you can see this is our image, right? In the initial moment, it will be starting from here, as the scanning direction given here is from top to down, right? So this is your object motion. It will be on the conveyor belt and it will be moving from, you can see here, as from bottom to top, and your camera moves from top to bottom. So you can say these splitted regions will identify, or you can say have a rough idea how your line scan cameras are going to scan the entire image, right, while moving. Now here we have in TDI, we have a combination of both CCD and CMOS, right? These both sensors are used here, and you can see there's a step-by-step conversion given here, right? The moment I have this entire grid, in the first moment I read only this row of pixels, and you can see there's some kind of intensity of a pixel of this entire row. You can say this is a kind of histogram, which gives you the intensity of this entire image. So this is my first row, and it is giving a pixel intensity. Second step, including first data, second step will be read and will be stored. So on, we have third, fourth, and fifth. And finally, after combining all these, we get the data, cumulative data of all row pixels. And finally, we can have the original scanned pictures. Hmm? This is how TDI images are being used. Hmm? Now, TDI techniques here can be easily used with CCD technology because there is less image noise, whereas it is more expensive and requires more power than CMOS technology, right? So there's a newer approach in CCD and CMOS technology, that is CCD based TDI imaging combined with ADMOS CMOS drivers, right? And that will be read out in a single chip. So if I'm having this kind of sensors for TDI sensors, there will be a circuit board wherein I'll be having TDI sensors, CCD image sensors, and CMOS image sensors in a single device, right? That will help me to understand the line scan camera operations, and it will be very more fast, high quality, and less expensive. Okay. So in few seconds, the session will be stopped. You join the new session with the same link.